Okay, welcome to the last California Dreams Technical Seminar Series seminar of November 2025. We are happy to have with us today Professor Ozdal Boyraz from the University of California, Irvine. Professor Boyraz received his master's and PhD degrees in electrical engineering from University of Michigan, Ann Arbor. Back a little later than I did in 1997 and 2001. He did a few years in industry and then joined UCLA as a postdoc, where he did pioneering work in silicon photonics and optical signal processing techniques. And then in 2005, he joined UC Irvine, where he is now a full professor. Professor Boyraz has done very important work in many fields, sort of based around silicon-based optoelectronic devices. And I won't read the entire list, but you have it in the bio here. He's co-authored or authored more than 250 journal and conference publications, holds 10 issued US patents, and has received awards such as the DARPA Young Faculty Award, and is a senior member of Optica. So with that, please take it away, Professor Boyraz.
Thank you very much, Steve, for the introduction. And hello, everyone. I assume it's all afternoon. Good afternoon to everybody. So today, I'll talk about the two topics, and then actually, first is mainly around the silicon photonics. The other is free space optics. But at the end, I would like to actually opportunity to present how we can merge the actual free space optics to the silicon also. So title is Silicon Photonics for Inertial Navigation and also Free Space Optical Systems. So as Steve said, I'm actually from the Electrical Engineering Department at the UC Irvine. So basic premise of the first talk is how do we measure the transaction or like a physical events surrounding us. And so when we talk about the physical quantities of interest, we are talking about when we are like environment, temperature, humidity, or presence of certain chemicals. Or if we are talking about mechanical or geometrical systems, we want to have distance, displacements, force, acceleration, vibration, pressures, or material properties, refractive index, density, viscosity, or absorption, fields. When we talk about absorption, there are different forms of absorption, of course. And if you are talking about the fields, electric field, magnetic fields, and the like absorption spectroscopy, and etc. So we need for all these quantities some transduction mechanisms, so we can take that and convert it to the electrical or optical signal for measurements. For example, for transaction mechanism for mechanical systems, either you look at the deformation or the motion, or electrical system, you look at the changes in the charge, current, voltage, resistance, capacitance, inductance. And in optical domain, the measurable quantities are intensity or power, phase, frequency, and polarization states. In the chemical domain, you look at the binding electron transfers. So these are the transactions or the mechanisms we can actually measure. So the silicon finds itself is an actually good candidate for optical transaction mechanisms, and which can interface with the many of those changes in the environments and then you can use it to detect them. And so when it comes to using the photonics, basically you can use the silicons, you can convert the electrical signal to optical signals by using modulators as we use in the communications, or you can generate the integrated photonic RF signal and processors. Optical to the optical, we look at the spectroscopy, like a refractive index sensing and lab-on-chip platforms. Or nowadays, quantum photonics basically use a phase, frequency, and polarizations and changes in the systems. And beyond that, we have many publications out there on the chemical domain, on-chip biosensor detecting the molecular bindings, and by using the silicon photonic devices. And then recently, for the last a decade ago, there was actually huge interest in the surface enhanced Raman scattering, or the SERS, and which used the silicon platforms to enhance the gas and chemical detections. And in mechanical domain, silicon has a lot of MEMS devices for and for gyroscope or other structures, or laser Doppler vibrometry. And also photonics has been used in fiber domain or integrated optic domain to measure the strain or structural monitor of the different architectures. So our interest is, of course, we are a photonics group. We are looking at the optical transduction and then use those for different purposes. In my group, if I just give a brief, like a 3-4 slides, brief outline of what I did based on towards that directions. And one of the project I did experimental and theoretically was the detection of the far infrared radiations by using plasmonic antennas and optical waveguides. And the other one is recently we have published theoretical and experimental results on plasmonic bolometers for, again, infrared detection and terahertz detections. And we had some nonlinear experiments. And the last one, which actually the focus of today's topic, which is the displacement detection and the gyroscope applications. If I just want to give actually one slide summary of what I did on the first three, and then I can focus on the last one for the rest of my talk. So in the first project, our goal was detection or the infrared radiation. This is one of the challenging problems, because when you go to longer wavelengths, like 4 microns or towards the 10 microns, then the finding and high sensitivity room temperature detectors is actually the problem. So alternatively, we said, can we use just the conventional optical devices by using some mechanical systems? And for that purpose, we designed plasmonic fishbone antennas, which is suspended on top of an optical waveguides. And those plasmonic antennas are bimetallic structures like a gold and nickels, which they have a different thermoelastic constants. When they are heat up, they pop up and increase the separation between the waveguides and the antennas. And when they cool down, actually they come flat and then get close to the waveguides. That gives us some evanescent field coupling and then loss on the optical field, which is propagating through the waveguide. And then you can use conventional photodetectors at 1550, for instance, and to detect the presence of the radiations. We did this design for the 4 microns, and that has been published earlier, around 2018, 2020 timeframe. And we did the fabrication and the noise characterization, etc. Our goal is this, actually. You see many experiments similar to this, and usually people present and chip scale devices. And yes, device sensing mechanism is chip scale, but when you look at the readout mechanism, how do you actually read out what you are detecting, is you see an optical table full of equipment to detect this. Our goal was to create a fully miniature devices which can do detection and then actually give us the readout signals on the same chip without using an optical table full of devices. So that's actually the one project we actually look at it for transduction. The second one was actually using the terahertz or far infrared detection. For that purpose, we use metallic plasmonic antennas, which is an absorber, highly sensed, high efficiency absorber for design for the resonant absorption at the certain frequencies. And then in between, we had a vanadium oxide nanowires. And that's actually hidden. Those who are not familiar with the vanadium oxide, which is one of phase-changing materials, and as a natural material, it has a phase-changing property around 70 degrees Celsius. and moves from semiconductor state to the conductive states. And then there is an almost like a 3 orders of magnitude change in the resistivity of the materials. So we use these plasmonic antennas to heat up, and then we bias this architecture at the transition temperature. And then we use a nanowire so that we know that the resistance is proportional to the length over the area, and then we reduce the cross-section area, so we get a very large resistance on the vanadium oxide for the constant bias current. Any change in temperature translate into a large voltage swing. And so we did that for theoretically for terahertz detection, and then experimentally we did a single pixel detection for the mid-infrared wavelengths and the fabricated vanadium oxide and nanowires and the patterns and etc. So that has been done, and actually in the recent years. So of course, the last one is is kind of poor man's optical waveguide architecture. We used the anisotropic etching to etch the silicon and deposit the silicon nitride waveguides, and then the silicon nitride on top of it, that wedges act like a waveguides on the knife edge, and then you can put some gold nanoparticles and etc. increase the nonlinearity of the system. So those are actually experiments I have been doing in the past, and these fabrications are done at mainly the clean rooms here at UCLA. And recently, as I'm actually moving forward towards the foundries, which is actually the relevant California dreams, and then we have a collaborated projects on inertial navigation. So, which is actually the first half of my talk will be on this part. So, what is the goal here? Goal here is look at an inertial navigation, which means actually track the motions and the rotations of objects. And there are many actually the mechanical gyroscopes out there. One of them is the design which is proposed by Andrea Shekel from the Mechanical Engineering Department at UCI, which use hemispherical shells and dual shell architectures. You can see it here. And you have an outer shell which is sitting on a substrate, and then there's a suspended inner shell. If there is any vibration, it creates an oscillation on this membrane, and then you can look at the resonant vibrations if that actually any rotation which cause an actually the rotation of that vibrational modes. So these are high Q resonators, and so we are talking about Q factor in the order of millions. And then oscillation frequency of these mechanical structure is in the order of around several tens of kilohertz. If you think about it, when they start oscillating, they will actually start oscillating several seconds to the minutes range. So they are very actually good resonators. But the problem is, how do I actually read out this vibrational mode and analyze these vibrational mode and create a sensible gyroscope or tracking mechanisms? And so that's actually opportunity. We had it, and then we are looking at it. Basically, what happens is here, this is actually the kind of flipped version of the architectures. If you have, this is the dual shell structures, hemispherical resonators, this is the part which is suspended, this is blue part. And when there is some perturbation, it starts oscillating. And then if you drive it at the resonant frequency, it will oscillate, and you are going to see deformations, which they call it the wine glass mode, and kind of expand and contract. And then you have the nodes and antinodes. Basically, those are actually the kind of fixed points are antinodes. And then you have the nodes which is expanding and contracting. And so if there is a rotation in the system, that mechanical oscillation is going to rotate also. You need to track that mechanical, identify the oscillations, the mechanical vibrational mode, and also able to track so that the system can work as actually gyroscopes. And so the inertial gyroscopes. So the question is, how do we do that? And then why do we do that? Why do we do that is actually this bigger pictures. You can take these multiple of these gyroscopes and then package it in some kind of small cubes, centimeter size of cubes, and then each one is measures the rotations at the certain planes, and then in the three-dimensional you have a full picture of the inertial navigations. And of course, having that multiple gyroscopes and necessitate that actually you need a kind of compact readout mechanisms and processing of these vibrational modes. And classical approach, which has been used up to now, they use a capacitive architecture, which means they deposit some metal films on top of that wine glass architecture or the hemispherical architectures, and then deposit electrodes at the bottom on the substrate, and a vibration changes the gap, and then you create an actually tunable capacitor, and then you measure the variations in the capacitance in the architecture, and then from capacitor you do actually the picture of generate the full picture of the oscillations mode, mechanical modes. And of course the problem here is that when you deposit metal, you lose the elasticity, and then actually the Q factor drops almost like 3 orders of magnitude in the certain cases. And so you lose the Q factor. So, and we need a mechanisms without degrading the Q factor, how we can detect these vibrational modes. So first we said, okay, can we do an optical, actually the readout mechanisms, and basically look at the edges of the rim and look at the vibrational modes, and then see whether we can beat the capacitive modes without degrading the Q factor. First, we did some simple calculations, and it shows that if you have some kind of vibrometer architectures, if you send in 10 milliwatts optical power, I will show the architectures, and depends on the reflection, how much reflection is happening on the surface, we can generate several orders of magnitude, better sensitivity and better SNR compared to the capacitive readout mechanisms without degrading the Q factors, without depositing any metal on the system. Of course, this is actually theoretical study. Glass gives a 4% reflective, but we look at the different reflectivity, like a 1%, like a 4%, or if you just deposit a metal, like a gold, which gives you 90-something percent, 98% of vibrations. So this actually gives an encouragement. This encourages us saying that, okay, yes, optical mechanisms can be an actually good candidate to detect these vibrational modes and provide a chip scale gyroscope without going through the capacitive methods. So this is an architecture we actually proposed as the first trial. We said, let's say we have one optical waveguides, and then we design an optical antenna specific ratings, which is designed to the height of the systems and eliminate the edge of that mechanical oscillator, and then collect the reflection here, and then it will combine with the second arm of this the architecture, interferometer architecture, which acts as a local oscillator, which creates a homodyne detection. We have the balance detector at the end, which is all in the silicon, and then created the detection vibration readout mechanisms. And so basically we did a theoretical study, like how much the displacement we can measure, what is the linearity of the system, which is another problem which I will come to it later on, and how much power we need for these SNR values. And it turns out that actually you can really very nicely detect the vibrations from something like starting from picometers all the way to like a couple of hundred nanometers very nicely with a very little error. But if you approach the 100 nanometers and beyond, and since this is actually the nonlinear readout mechanism, transfer function is cosine, you see some nonlinearity. So higher harmonics starts showing up, and then you can actually lose you generate some error in terms of measuring the total displacement in the system. So overall, theoretical results show that we can start from picometers range all the way to 100, let's say 100 nanometers amplitude of the displacement, and then we can measure it and then linearly with very little error at the end. So that's what actually we find out, and then we put actually into the fabrication. And for this, there are several components. We designed ours, like in grating couplers, and then some of them we used the PDK files from the AIM Photonics. And the first architecture looked like this. We have an edge coupled fiber coupled through the edge, and then laser comes from outside, and then it half goes to the gratings and then collect the reflectors, half acts as a local oscillator. We have actually this interferometer here and the balance detector. On the board we have our own TIA design and lock-in amplifier or oscilloscope. In a real time we can measure the vibrational modes. So this is actually, we designed this architecture. We get actually the first fabrication results, and of course when we designed this, we had to actually, for grating parts, we had to pay attention to actually the distance. Eventually, these are going to be bonded on top of it. PIC is on top of the gyroscope. And when we do that, we are going to have basically waveguides, and then there's an about 5 micron gap, and then about 500 micron glass substrate, and then we have the edge of the rim. But in reality, for the test we have it's not bonded yet. We have some about a 500 micron additional air, so the grating is actually, the separation is optimized for this configuration. And then again, we have a glass substrate and then the rim. So for this configuration, basically, we have about 130 micron spot size based on this grating design, which is hitting the rim, and then coming back to this collection antenna, and the rim size is in between 100 and 150 micron range. So this is basically the whole architecture. This is the microscope image of the structures for the gratings. And then we take this, and then one vacuum sealed gyroscope, the hemispherical resonators. Of course, the Q we are actually using testing at the moment is not as high as 1 million, but these are actually in the order of a few thousands of Q values. And that actually, the resonators attached to the piezo structures. So the piezo vibrates and then initiate the modes, and then we come up from the peak from the bottom and then measure the vibrations on the peak architectures. So this is actually, this figure on the right side on the top basically shows what the architecture looked like, and when you look at underneath here. So we have on the top piezo, and at the bottom is the optical peak, and we have about a 0.5 millimeter of, roughly, because of the wire bondings, we cannot get too close. And so we have this actually the gap in between, and then so this readout mechanism. So this is actually the picture of it. You can see we have several pictures. These are the gratings, and these are the one is transmitter, the other is the readout, and this is the second PIC. And then we have the detectors and this architectures, and then we actually measure the vibrational modes. So we have I will show the results for the single point and the 2-point readout. And we have a new chips which is coming, and then we have a multi-point elimination detection mechanism. And also we have a reference, because there is some background vibration due to the piezo. We want to suppress that by reading actually outside that membranes, vibrating membranes. So nodes and antinodes theoretically separated by 45 degrees, but you don't know where they are exactly, because when you bond it, you don't know where the mechanical oscillations are actually, or the exact location of the nodes and antinodes. In a perfect ideal system is you have total degeneracy. You have no control on the exact locations of the actually where the expansion and then actually the null points are going to happen. But some defects in the fabrication might actually dictate the specific locations. So this is actually the architectures. So first thing we did for the single point illuminations, we get these chips and then put it on an taken resonator, and then first measure the resonator with a well-calibrated laser tabletop laser Doppler measurement systems, LDV systems, and that shows that basically applied, this is the magnitude of the piezo voltage, and this is the displacement. It has a very linear scale, and you can see up to from 0 to all the way to the 500 picometers displacement. And then we actually take this and then apply to our PIC systems. Of course, here we don't have a calibrated software like in actually the tabletop LDV systems. We just read the voltage level in the transimpedance amplifier after the balanced photodetectors, and then we can do mapping one-to-one, but we have exactly perfect linear, and then error is on the order of actually the percent level in average RMS error. So this gives us actually good encouragement, saying that actually we can detect the picometers of levels of vibrations and with a very good accuracy. And so we did actually the calibrations in this. And so our estimate was in the order of a few picometers. So we started with a perfect mirror-like gold-coated piezo architectures, which gives you something like a more than 90% reflection. And then if you assume that the 6 dB SNR is a good SNR level for detectability, and we said that, okay, with the good reflections, we have 1.9 picometers, or let's say 2 picometers of sensitivity in our systems. And that gives you basically measured, assuming that, if we go back here, we have a 10 milliwatt here, and then 5 milliwatt split it to here, and 5 milliwatt and 40% of the 5 milliwatt is radiated. And then we have about glass, which is about 4% reflective, and then whatever is reflected, actually that's a perfect uniform surface. This is not perfect uniform, but there are some scattering also, but let's assume it's a perfect uniform scattering. And then it comes, and then we have a collection efficiency of 40% right there, and then it goes to this interferometer. So that means you collect only 16% due to the grating efficiency, and then we have additional loss of 96% due to the reflectivity. Basically, we are collecting almost like a fifth, losing almost 5 orders of magnitude of the power here, and then using the system and then measuring it, and roughly is with a for glass surface, for gold surface, of course, reflectivity is high, but the glass is about 4%. So 2 picometers gives about 6 dB SNR, and then if you just increase the driving voltage and then increase the vibration to 3 picometers, you get almost like a 30 dB SNR in the measurements. So since we know that the calibration from these measurements, we can project on the glass, and saying that for 6 dB SNR, we can have sensitivity up to 10 picometers, which is actually a very good number. And if you want to increase that, we need to put a little bit more laser power. And also we have a design on this optimization splitting ratios, and then take the saturation of the detector, etc. And then maybe we can actually have a gain and a few more dBs, and actually factor of 2 or 3, and actually improvement in this minimum sensitivity for the given power levels. So, and then we actually take out this piezo and then put the resonator and look at the resonant structures. So these resonant, the hemispherical shells, which we are testing, was resonant at the 34.664, and then it has an actually frequency splitting, which is second resonant mode is about 126 hertz away. And so it is very sharp resonance. And even though this Q is in the order of few thousands instead of millions, you can see we have an actually tiny bit of piezo vibration. It causes large resonance swings on that rim of that resonators. And so you can detect that, and then as you move away from that resonance peak, you see the vibration dies out to the noise levels. And then if you go back to the second peak and antinode, and then you can see an actual vibration at that location also, and it dies out very quickly. So this is an actually excellent match with what our system is working, and then tabletop LDV is working. They are exactly almost identical in every aspects. Of course, when you are actually down to the hertz level, your measurement system and then actually the quality of the frequency generator matters, because we are looking at the hertz levels of drift that can actually, if there's an error at that level, it can be attributed to any of the actually components we are using in measurement systems. And we also tested 2 points, as I said, 45-degree 2 pictures, and you can see and catch one of the vibrational frequencies, but when you go to the second frequency, one of them seems like on the anti-node, and you cannot catch it, and then the one is actually measurable, the other is not actually is not readable. So here is the problem is, of course, these are not the bonded structures. We are relying on hand adjustment, like alignment of the rim with actually those grating architectures. So, and this is actually the trial of several hours, and eventually you catch at 2 points, and you say that, oh, these are close enough, and then their 2 gratings are eliminating the different points of the rim. And we don't have an exact and very good control on are we really hitting the center of the rims or the edges of the rim, etc. And so we just optimize for 1 point, and then the other is kind of hand waving our arguments. And this is actually one of the best results. But there is in parallel work going with an Integra, which is they are trying to do actually the packaging, like a bonding of these architecture with the ASICs and then PIC, and hopefully one day we'll have actually the perfect alignment and then actually good readout from the multiple points. And so these are actually key experimental results for this project, but at the same times, we are moving towards an optimization. Number one is the gratings, trying to make sure that the radiation efficiency is very, very good. And so that we have a much better sensitivity in the systems. And also, as I mentioned, that the linearity, so that if the displacement value is from picometers to like 100 nanometers, you have linear response. You can take the voltage to nanometers easily with a 1 or 2% error. But if you go beyond 100 nanometers, then the transfer function is nonlinear, and then there are some of the energy is transferred to the higher order harmonics, and then we have an error in the reading of exact displacement amount. So there's actually the new design, which is in the fabrication right now, which is IQ detection systems. We look at the in-phase and quadrature points and decompose that so that we can have a linear reading from picometers to micrometer range, map the vibration voltage readings to directly to voltage readings to the picometer distance variations on this. This is important because when in real life, there are so many different perturbances on the moving objects, and that can lead to large swing on the vibration oscillations of these mechanical resonators. So with that, actually, we are going to address that, and then we will get in 6 orders of magnitude range in optical domain. But if you translate that to the electrical domain, because the power is going to be squared, and you will have actually the 12 orders of magnitude dynamic range in the system. So that will, of course, require a new design on TIAs, because these are slow things, and we need an actual automatic gain control. So that will to accommodate like a 12 orders of magnitude variations in the current entering the TIA. So that will be an actually ASICs part, but we are interested in the optics part by using this IQ modulation architecture. So this is actually in phase, and so we are moving towards on this project basically, and from passive readout towards active, and also steer the beams and then at the different points of this gyroscope architecture, and then have an actually readout at the different points, nodes and anti-nodes, and then create a full pictures of the mechanical oscillations. And with that, before I switch to actually the second part of my talk, is there any question I can answer at the moment?
There is one question, and the person asks, how many points can you illuminate simultaneously? And they're referring to slide 17.
Okay, so this. Okay, so first of all, how many points we need to eliminate? So if you have a very good SNR in the systems, 2 points is actually the necessary. But what we are actually trying to do is, in our systems, considering that the noise in the systems, we want to first have the reference point eliminate onto the systems, and so that will measure the background outside. And then we want to basically at least 4-point eliminations within a 90-degree or from 0 to pi orientations. And then few of them are 45-degree separations, and then one is intermediate separation. 45 degrees is the separation between the node and anti-node. And if you are aligned perfectly, that will give you actually, the one is giving the oscillation, the other is going to give the null point. But you don't know where actually those nodes and anti-nodes. So we can use some few other samplers, and so to identify where the exact location of the nodes and antinodes. So coming to the question, actually the answer is ideally 2 is enough, but practically we are looking at the 5-6 points, and mostly they are separated by 45-degree, and then, for example, for this design we use a 0, 30, 45, and 90 degrees, and hoping that we will have a full picture of it, and then plus that reference to suppress the background. Any other question?
I think we're good for now. You can continue.
Okay. So second part is related to, actually, this is a separate project, and we are part of a consortium, and which is the rural area wireless broadband access. And this scope of this project is that you create an low-cost wireless access to the rural areas, which there is no fiber, so fiber deployment. And then we are actually the Amazon, actually the Photonics group, who design a free space optical communication unit, and which gives you backbone optical network, and then you have a wireless antennas at those locations. We are part of a large consortium. This consortium is led by the Iowa State University. There's a rural area, and they have actually several locations of different, like a 5G and 4G, and then different Aviat antennas and etc. wireless network. And then we have right now 2 is deployed, and then actually 2 is shipped, waiting for deployment, and then another 2 is being actually the package for final tests are conducted and shipped for final deployment. So what we have is this a custom design optical node. We call it this RNet architecture. It's a publicly available actually network architecture, optics and all the RF architectures. And we have two nodes. This is a custom design optical network. And so two of the nodes, which is one of them is at the roof of the dormitory. This is actually our design right there. And then the other is so-called agronomy farm. This is a one farmland. We have 60 feet pole, and there are optical nodes and wireless antennas around it here. So this architecture basically use commercially available RF fiber transceivers, and then an optical switch, and then provide an 10 gig multiple channel 10 gig transceiver transmissions and receiving capability, and as an fiber backbone network, replacing the fiber backbone networks. So this is an architecture, and we design. This is the nodes actually we develop, and everything is actually in-house. And the collimators we bought it, and some of them actually we fabricated. And so architecture look like this. And we have one actually the main antenna which sends to the 1550 nanometers communication signals, and then on the same antenna, same telescope, we have a 980 beacon light. And the whole idea for the beacon is for two purposes. One is help to the alignment by using the camera, which is sensitive. The CMOS camera is sensitive to the 980, so we can use to detect that incoming light. And also, and we have an APD with a wide angle receiving angle. So low speed APD, which up to 1 megahertz, and then create an actually the supervisory communication. Basically exchange the protocols, tell the other side, even though you don't have an actually the communication with 1550, other side to do what to do, like tune the actually your orientations or some other actually exchange of the commands. This is the architecture we have. We have a camera for alignment, APD for alignment, and also for communication. And then we have the main collimator for beacon and laser communication in the systems. This is actually basically control algorithms and APD and the camera. Look at the beacon lasers, and then we have the transceivers power readout, and then tells us what is happening between the main collimator or the main antenna. So this is an architecture we have built, and this is deployed almost like 2 years in Iowa. And we have several tests going on in the systems. And so, of course, when we actually put this the system and then deploy in the field, you're going to see a large swing in the optical power due to the scintillations or atmospheric turbulences. And you have very little optical coupling to the fibers. And transceiver sensitivity is in the minus 424 dBm. And you are just a little bit above the transceiver sensitivity. And that creates actually the frequent channel dropout because of these vibrations. And it's not the average power. It matters because if you look at the signal, and you can see that it's about the receiver sensitivity, but this dynamic range of the oscillation is the one which causes a lot of problem, because that transceiver tried to adjust its receiver sensitivity or the decision point, and suddenly power fluctuates, and then it starts again the calibrations, and it overwhelms, and eventually it gives up. It's after several tries, and then all the transceivers start giving up, and then actually you will have actually the dead communication channels. We did that actually to some low noise amplifiers before the receivers, and that raises the average power levels well above the receiver sensitivity, but still that dynamic range of the oscillations and overwhelms the receivers, and then actually cause and actually the channel dropouts. So we did actually several tests, and tests are still going on for various configurations. With all these channel dropout, you can get up to like by using a 10 gig transceiver, effective bit rates can be in the order of 1-2 gig, and we go up to like a 2.6 gigabits in in a turbulent weather. And the separation we are talking about is right now is actually the 10 gig. And this is what I'm showing here. And it does actually the communication. And if the fluctuation gets too frequent and too large, and then just the transceivers gives up and reset everything. Sometimes you need to reset the switch to the recover and the whole communication system. So this is actually done by using some hyperf test and by using like a pseudo random packages from one end to the other end by using a 10 gig communication links. So there isn't actually the genuine interest, but these results, so the time is running out. And so these results shows that basically there is an fundamental bottleneck, especially when you are relying on the commercial transceiver architectures. And to give you an idea, so what we learned actually, number one is the mechanical stabilities, which is an obvious. You need to mount all these things, and even the wind is hitting the architecture, the systems, it should be rigid and mechanically, so it's not vibrating. But the bigger part is the scintillation. This is actually the camera picture of the scintillations in after 10 kilometers. You can see beam wandering, which is right and left, up and down, and also scintillation, and then it goes bright. And so you can see the telescope and the fiber tip image kind of, and actually the other end after 10 kilometers. And you can see that actually the power goes up and down. And so this is actually the camera capture of the scintillations or the intensity pattern on the other hand. But we are not actually capturing. What you see here is not actually the camera picture. Camera is, yes, it is oscillating, but if you look at the rate of the power fluctuation is much, much slower than this one. And the dynamic range is actually is better compared to what you are seeing right here in the power fluctuations. So that means basically, and so we have fluctuations, but at the same time power, when you actually put that power into try to couple into the fiber, and that scintillation kind of loses the coherence of the system, and you lose a lot of power into the system. So we have a couple of mitigation mechanisms. One of them is so-called the MISO architecture, which is being tested right now. And the MISO architecture says, instead of using one transmitter, can I split the same data and split it into the 4 transmitters and then send it. So each transmitter is going to sample different section of the atmosphere. So then you average out to the scintillation effects. So that is being actually hypothesized. And then actually we did build again the custom design. And so this is actually the mechanical SolidWorks design. We have multiple transmitters here in the center single receiver. Again, we have the camera, avalanche photodiodes, and for the side channel communications and alignment purposes. And we have now a large mirror to steer the systems. And so we have now is actually the new nodes, which is being actually tested. 2 of them for, again, single transmitters receiver is being sent for deployment. And this is actually without the metal cover. Okay, when you put the metal cover, you have this very nice looking structures. It is a heavy architecture, but it's a good looking architecture, I can say. And then we created these architectures. So these those openings are the 4 transmitters. Center part is the receiver, and here a camera, and then you can see avalanche photodiode housing, all of them without assembly parts right there. So we did this the architectures again. By using stabilizing the mechanical oscillations, we tested with the 2.1 kilometers. And then we go on to even for alignment, we use a retroreflector also. And we use and test it for the 4.2 kilometers. And so the SISO is basically like a single transmitter, receiver is much, much better. And then even though we have a scintillation, we have a very good 10 gig transmission. Right now, actually, we are testing the same architecture in the 8 kilometers in California. One node is in the rooftop, and there's another in the mountains nearby. So it's about an actually 8 kilometers link we are testing. And then MISO is a little bit problematic because we need actually enough divergence of the beams. So and so the power level seems like not as good as the SISO at for short distances. But for 8 kilometers, we are hoping that the MISO is going to actually surpass the SISO architectures. For 4.2 kilometers, again, we get an actually effective like a 10 gig communication, but we see actually some channel dropout in the architectures. Of course, up to here, there is nothing actually relevant to the silicon photonics. And then actually the next part, which actually I would like to propose an idea. And then actually I'm hoping that in the future, there might be some interest in the collaboration on this area. So what you see here is, again, if you go back to the scintillation results, and most of the time is energy is there. So we are not actually losing the energy, but we cannot connect into the fiber because we lose the coherence of the systems. The coherence means we have a randomization into the k vectors of the systems which is hitting on it. And so this is basically is equivalent of the multipath interference in RF domain. So the beams are coming from different direction and interfere, and then you create a null points on the receivers. And the question we ask is, okay, when you create a null point, where does the energy goes? So energy is still there. It's just coming from a different channels, and energy is still there, but you haven't, where the fiber is, you have a null point. And so the question is, similar to Mach-Zehnder interferometer or Michelson interferometers, if there is one like a constructive side, there is another port which gives you destructive. And if there is a destructive side is on the detector, the other port has the energy, which is has a constructive energy. So can we create actually the system and kind of read the signal and actually two ports of an interferometers detect at the same time and combine in electrical domain? In other words, can we design and actually the silicon architectures? Again, the TX part is heterogeneous integration. We have the lasers and then modulators on top of it, and then gives the fiber out, and then there's actually the ASICs onto the silicons, and the receiver part have a silicon, and then directly come onto the silicon systems, and then send it to ASIC, and then gives to the networks. So this architecture was actually we were proposing is using actually the multiple gratings, and the gratings are, this is not a good pictures, and so basically each grating reads to the beam with a different optimized for the different k vectors, so that if you have a diversity of the k vectors in the for the incoming beam, so even though you have a destructive interference in one of the gratings, you will have a constructive interference on another grating. So can we do actually the architecture like this? This is actually the layout design. We have actually the grating part. We are still optimizing. This is not actually the final version of it. And then use actually the multiple detectors and then combine in electrical domains. And of course, we need to do actually the timing adjustments and etc. And combine in electrical domain so that actually that fluctuation we see can be minimized on the electrical domain and then minimize the channel dropout. I think waveguide detectors on the silicons are mature enough, and then now we need to actually optimize the architectures, and then I think that can make actually a huge impact for free space communications. Of course, we need to actually the fill factor. This was the gratings we have designs. You can actually bring them all closer together. If you use AIM Photonics, they have some actually gaps, extra gaps, which we need to trim so that we can bring them all of them together and then create a multiple grating but a large area detectors. typical 10 gig detectors are few microns of diameters. And then if you combine multiple gratings, you may get an actually the detection area, still a 10 gig or 20 gig or 40 gig detection, but the area is in the order of effective detection area is in the order of half a millimeters or so. So that will actually increase the reduce the dynamic range and increase the SNR significantly. This is actually the part actually I'm working on it, actually optimizing the systems. And if anybody interested in the ASICs part or actually even the photonics part, I'll be more than happy to actually collaborate in this project in the future. So with that, I would like to thank everybody and then thanks for the Caldereams for the opportunity to actually for the presentation. And these projects are actually funded by its free space part, initiated by the 1R, and then also is funded by the NSF, and then actually the gyroscope part is actually funded by the NCMS through the Army Research Lab. So we have actually, I would like to thank the sponsors also. Any question from anybody?
Thank you very much, Professor, for your talk. If anybody wants to put their questions in the chat or raise their hand and we can take you off mute, we'd be more than happy to do that. It looks like there aren't any questions at this time. So, Professor, I guess you did a really great presentation. This will be posted to our YouTube channel shortly after. Next week, we are off for the Thanksgiving holiday, but we want to thank everyone for joining us. And on December 5th, we will have Professor Priya Panda from USC joining us. But thank you again to everybody. Have a great holiday, and thanks again. Have a great weekend, everyone.
Thank you.
Thanks.